It's very nice to be here in person. I think I came probably a month before the lockdown, if I remember right, February 2020, I think is when I was last at this Blackboard. But so I do it in hybrid format. This time I'll also go back to the Blackboard, but I want to spend first some fraction of the time, which of course will depend on you folks, but some fraction of the time giving a broader picture because it's a bit involved. So I want to at least try to convey that bigger picture. And then I want to show you one very simple calculation on the board, which I think is sort of the in a way. So this is based on some set of papers, which the first one will hopefully be out in a couple of weeks, I hope. This is with Edward Mazenk. He's a postdoc at Chicago, a very bright young string theorist. So the three papers, and I'll focus a lot on this, but in this overview at least, and then depending on interest, I can say in the overview I'll mention a bit about the things here, but then depending on interest, I can explain. So the title. I think people would agree that the simplest large N theory is just that of an n by n integral of a single matrix. So you can consider the famous Wigner Gaussian matrix ensemble, and consider this class of gauge invariant, so say, observables, single trace observables. And this is actually a very, I mean, even though it's a trivial Gaussian integral, the large N expansion organizes it in a fairly non-trivial way. The combinatorics essentially is what the Feynman diagrams, the big contractions, essentially capture the combinatorics of the large N of the expansion. It's basically, in some sense, the skeleton of the large N expansion that you find in correlators like these, and this is something you can compute. There is, if you wish, a set of numbers labeled by the positive integers L1 to Ln, and I have omitted here the genus, but there would be a genus G contribution. And one of the things, the concrete thing in this talk will be to argue that this set of numbers, so infinite list of numbers, is captured by dual string theory, worldsheet, which has a bona fide worldsheet description, which I will explain to you. And in that sense, it's sort of the simplest version of gauge string duality. By the way, so many of you who have studied the large N matrix, large N theories would be familiar with the classic paper of Rajesh and Parisi and Zuber, which showed how in the large N limit and later beyond as well, you can solve for this. So this is a case where you can actually, in a sense, go away from the free theory, go to an interacting matrix model. And of course, there are a lot of developments to do with taking a double scaling limit of this potential and so on. But what I will be emphasizing here is, as I said, we'll have a list of observables. So if you wish, there is this list, which are essentially numbers indexed by these L1 to Ln. So this list will be, should be captured by a dual string theory away from any double scaling limit. So without any double scaling limit. And in that sense, I want to want to propose that it's a kind of a very stripped down to the essentials version of gauge string duality, in which you can actually work at this tensionless limit, which is what I will mostly focus on. But by this philosophy, as will become evident, you can go away from the Gaussian also. But
so sorry,
yeah.
Just at finite n, you take some matrix integral like that,
and then do a 1/n expansion. Yeah. So we will organize it in the of the expansion. So this is what numbers, by the way, are very non-trivial. Even at genus 0, about 10 years ago with a student, I think for the first time we wrote down explicit formulas for some combinatorial formulas for this for arbitrary L1 to Ln. No, actually for even L1 to Ln. It's not even known for arbitrary L1 to Ln. So
these are the connected
correlator. You can define a few variants, connected, normal ordered, and so on. Those will be details, will not matter. But connected correlators, you want to keep.
So I'm sorry.
Yeah.
I mean, so you mean the answers were not known sort of beyond leading order in something.
The answers, you can compute some correlators, and I'll tell you a little, but the goal here will not be to compute anything. It will be to show the equality. So firstly, yes. So let me say definitely there's some set of things that are known, but explicitly not very much. I mean, there are implicit forms of computing these and so on. So it depends on how explicit you want to make it. But the point here will be to propose a dual string description, a worldsheet theory, which will have observables that will be equivalent to this. And that will reproduce this.
Just to say, the crudest thing would be to take, disconnect. That, of course, is
large n factorization.
So I suppose the first connected thing.
Yeah. So it's always that.
As you all know, connected two-point density correlators, so on are unknown, right?
Yeah. So exactly.
Something
unknown, but arbitrary endpoint functions and so on are not.
So just one more thing, since you're not doing double scaling limit, you're still going to get a string voltage.
That's what I want to propose. That I think it's an unusual one. It's an unusual thing, and there'll be several unusual things. Yeah. I'll give you an explicit worldsheet target space sort of proposal for that.
This is the solution going to be called a prediction.
So we'll see that we can write things for an arbitrary generating function of these correlators. So you can exponentiate it. So in that sense, it's sort of general.
So Rajesh, related to Shum's question. So the second scaling in the down scaling, what that did was that the number of triangles in the simplified
became dense.
So that became infinity. But now you will have a finite number of triangles in your.
There will be one presentation in which there will be finite number of triangles. What I want to claim is that these are not invariant notions. That there will be one presentation in which you will get contributions from discrete points on the moduli space. But there will be another presentation where you can write it as an integral over moduli space in a more conventional fashion. I think these just require by total derivatives or something like that, presumably. So I think it was all a bit of a red herring. I think this whole thing of having to take that continuum limit. It was nice, and you get a simplified version, but I don't think it's strictly necessary. That's a good physical way to maybe think of the double scaling limit. And we'll see a bit. There's a sort of a related BMN-like limit I will talk about, where you take all these numbers very large, L1 to Ln very large. And then you kind of also reproduce this sort of continuum. But I would like to actually do more. I would like to derive such a duality, not just propose such a duality, in a way such that the equality of correlators starting from, say, the Gaussian integral becomes manifest, that you can sort of go some way at least towards reconstructing the dual closed string starting from this, because that would be the sort of way to try to understand how Largen theories sort of give rise to closed strings, at least in the first case. And in some ways, there will be connections, and but I don't still know the full picture, but I'll try to say this thing about relations to the ADS3 and ADS5 tensionless limit, the free theories. So in this slides, what I'll try to give is this sort of the overall picture. So I'll sort of first just propose it. I'll just make a bold statement of the equality of some dual string theory. Then I'll try to explain, and this will be sort of most of the talk here. This time will be, in a sense, verifying it. By that I mean that arguing why this set of numbers are the same as another set of numbers coming from string theory, which will use a lot of earlier work, actually, a lot of work from the 90s and a lot of work done here, actually. So that is there'll be a bit of a convoluted chain of logic there, which I have to try to make clear, which is why I try to use the slides. And then, if there's time and interest and so on, I'll sketch. And this is still, we can go, I think, quite some way towards a derivation. At least, I think all the essential ingredients of the dual string theory we can see from the matrix integral. And then finally, I'll try to embed this in the larger 8-string duality of n equals 4 units. That's sort of the plan. So let me make the proposal. So I mentioned these correlators, genus G. So there's two descriptions which actually just mirror symmetric duals to each other. They're both topological string theories. One is A-model topological string theory. A-model topological string theory is typically on a Calabi-Yau. You define it a Calabi-Yau, but actually all you need is a CFT of n equals to 2 worldsheet CFT with central charge equal to 9, what Calabi-Yau has. So it need not be a Calabi-Yau. It could be any n equals to CFT. And so the particular one that we consider is something that has been considered a lot in the literature, at least in the 90s and 2000s. And so on. It's what is called like a Suzuki-Cosette model. It's basically a cigar-like geometry. SL2R mod V1. Cigar-like geometry, and in which we'll actually, in our case, for the Gaussian dual, you have to turn on a certain background of a certain marginal operator, kind of a winding, not a winding, a momentum operator. And this set of numbers will be given by certain correlators of physical observables in that this thing. So this will be some, and this one. In the A models, there will be a cigar-like geometry with some actually momentum mode of the self-dual. So okay, I'll say. But one thing I just want to point out to connect with more things I have been doing recently is you see this SL2R is at level 1. The SL2R Resumino-Witten model is at level 1. That's what is needed to get that central charge of 9 that I mentioned for the critical. And SL2R at level 1, we have learned in recent years, has very unusual properties. And this was what was behind my work with Eberhardt and Gaberdiel, in which we showed that unlike in the more general ones, there's no continuum of long strings. So the SL2R level 1, at least is the bosonic, normally would be thought of as the bosonic part of ADS3 times S3 world sheet theory with NS flux. So 1 unit of NS flux, and that is sort of the tensionless limit. So and so some of the insights that we have learned about the SL2R theory at level 1, I think will play an important role in this. And it was quite a surprise for me that it's precisely that level that appears here, which is needed for many of these. Yeah.
This course itself contributes central charge line of this course.
Yeah. Supersymmetric cosine. N equals to cosine.
So if you wanted physical string theory, that would be at a different level?
Yeah, if you wanted it, that's the one that is the usual black hole geometry. And that is at level some 9/4 or something like that, which gives you an C equal to 10 or 15 or whatever, 15 or 26 or this thing, the one that Gautam and others study. So this is not the black hole geometry. It's not the black hole background. It's a different twisted.
This is also the one that appears for the spine.
Yes. And there's a B-model version of it, which is a little less geometric. It is given in terms of so-called Landau-Ginzburg potential. You consider people may be familiar with the fact that n equal to 2 minimal models, n equal to 2 just ordinary minimal models are given as the infrared of some Landau-Ginzburg theory with potential z to the k plus 2 or something. So this is a version of that, but it has a 1/z potential. And this is something that had been proposed, and this had been studied in the context which I'll describe. But Hori and Kapustin, for instance, long ago when they were considering mirror symmetry as one of their cases, was the sort of dual between these two. So it's established using the usual world sheet mirror symmetry.
Also linear dilaton on the side?
Which side?
The LG side?
LG side is just a superpotential with this coupled to 2D gravity. And there are
T. What is
yeah, so these are observables in that theory. In the normal n equals to 2 minimal models, you know that the observables are some phi to the n. N goes from 0 to k or something like that. When you couple it to 2D gravity, there are so-called gravitational descendants of that. You have to sort of dress it with 2D gravity fields, which when you have an inverse potential like this, then there are then you have more observables, because now there isn't, the chiral ring is not finite in some sense. So you have more observables and you have to dress it. But these are the corresponding dressed chiral primaries of the n equals to theory.
Just roughly, if we were at some other level, some more usual level, there would be the asymptotic region that go down the cigar, and that should be then reflected somewhere on the other side. And some asymptotic region with a continuum of states.
So here there's no continuum of states
because we're at this level. So this duality works exactly for the level
this particular level. It comes through something else, which I will just now spring on you in the next slide. So this the verification. So what we want to ultimately do, and which I'll try to say how, is how to go directly from here to here to here, or here to here and here to here, both independently, sort of in a constructive way. I'll try to explain how you can do it. But the way we'll try to verify it will go through some auxiliary things, which will be useful as a way to sort of understand why there is this equality. But we'd like to later get rid of them. It's like superstructure.
Just see the two models.
Yeah.
And on the B-model side, is there a simple way to see the SL2R response?
It's a good question. It's not SL2R. I mean, there's. I mean, this is it's an SL2R mode U1, so it has this sort of cigar-like this thing, but as global symmetry, there's a overall global symmetry. Yeah, they should be acting on the primaries in some way. But let's see. Things carry the same charges, so the U1 charges on this thing, but the overall SL2Z I think has to do with this. SL2R has to do with this form of the. It's a good question. I'd like to think about. So, okay, so this was the top line that I said. Now, let me try to explain the kind of convoluted logic by which this sort of follows, and if you want to actually verify. So, what we will show firstly, and this is a calculation I'll show later, is that this matrix model can be written in terms of another matrix model, which was actually proposed by Sunil and Camillo, with a certain deformation, and this will be a sort of go through something that I'll call open-closed, open triality, which I'll explain later. But anyway, this is an equivalence of matrix integrals, which we demonstrate very explicitly.
But the latter one could be at finite L.
Which one? This one, yeah, there will be at a different thing. Yes, it's true, and we will. If you want to sort of see the full phase space, you'll need to take that one also to infinity. If you want to kind of get arbitrary correlators, arbitrary bound. It's like the analog of what in the double scaling limit was this Kontsevich matrix model. So there was this double scaled matrix integrals, and then there was this Kontsevich matrix integral, which had the similar feature that you finite a large n in that, but that could be a different distinct in principle. Yeah. And so that's why this is related to some kind of a deformation also. But why did Sunil and Camillo propose this model? Because this was a matrix model that captured the sequel to one string theory at self-dual radius. So the sequel to one string theory, which is the non-critical string theory, bosonic ordinary string theory at self-dual radius, has sort of momentum modes, which are as a discrete spectrum of physical states, the momentum integer quantized, and people had studied the scattering amplitude of these so-called tachyons. So they were called tachyons there, even though they are just Marslet fields. But you can consider the scattering amplitude of tachyons, positive momentum tachyons, negative momentum tachyons, indexed by a single integer only. The people had, I think, these people had written down an S matrix or a generating function for S matrix, and this matrix model actually captured that scattering amplitude. So it's a self-dual radius. We need a certain deformation of this, as I said, which corresponds to turning on a tachyon of momentum 2, so to say, in the units where the 1 is the simplest or this
self-dual radius time is time is compactified?
Yeah. So there is the dilaton field, and then there is the X field, which is the.
And then you compactify time and then compute an S matrix.
Well, I mean, you can compute sort of the you compute the amplitudes of putting in the. So you have these momenta, and you consider the scattering. You consider the amplitude, if you wish, of the scattering of these. Momenta, you put these on-shell vertex operators and just consider that.
What, do they have pointing as well, or just
no, just momentum?
Okay, so then you're choosing
to really matter.
That it's self-dual
really matter.
Yeah.
But the quantization and everything matters, and So this string theory in this background has been well studied in the 90s. A lot of it probably forgotten, but people in this room remember. So this string theory, in fact, had been also proposed to be related to by Sunil and Kunran to be related to the Kasama-Suzuki matrix model. But this, and later by various people, again, Indian connections, Sujay Ashok and Samir Murthy and Prost and others, showed why these two are related, because you can use this, you can use a parametrization of the coset and show that the scattering amplitudes of this theory are the same as the scattering amplitudes of this topological twisted theory, because they're both sort of they're both two-dimensional, as you can kind of roughly at least see. This equal to one theory. It's also 2D string theory. There's also a 2D target space, and roughly there's a kind of a linear dilaton like thing.
Sorry, they carry Euclidean momentum in time or Lorentzian momentum? I mean, do they carry real Lorentzian energy or
They carry Lorentzian. They're on-shell states from the point of view of the 2D string theory.
So the compactification is in Lorentzian time.
Yeah, if you want to incorporate that way, and I mean it's.
Or can I just forget the compactification?
Yeah,
I just
think just forget about the compactification because it's discrete momenta, and you just compute a scattering amplitude in 2D string theory. It's a standard worksheet computation of.
So the self-dual radius is just by choosing to scatter
these momenta, and those are the physical momenta, and no others are sort of created.
Yeah. Okay.
So in the 90s, there was a lot of work which actually then Sunil together with Devashish and had also proposed this 1/z potential. Here we have 1/z plus this deformation. This is the deformation I was talking about. So there was this whole connection to these, and then there's a relation to the conifold geometry, etc. Which, but the main connection is through the main way in which you can see that these correlators must be equal is through the equality of this matrix model, which reproduces the equal to 1 scattering amplitudes, which are the same as those of these two theories, which you can show. This is a more and this is a closed string sort of equivalence of closed string quantities. So that's roughly the chain of the logic that allows you to show that these are exactly the same as this. But as I said, here I want to tell a little story.
Sequence 1 is also just matrix quantum mechanics.
Yeah. In terms of that discretized theory, right? I mean, the double scale quantum mechanics.
That's not going to play any role.
That's not at least obviously going to play any role. I mean, it is an interesting question what role it plays. In this thing, I should say one thing that will be there is that there is this so-called cosmological constant in the equal to 1 string theory, which was related to how you take the scaling limit to the Fermi surface. The relation, so here we are, so that plays the role of the genus expansion parameter. Here we will have the genus expansion parameter as n. It's uncomplexified. The n will be related to that mu, or the cosmological constant by a sort of a complexification. So I don't know what it really means, but just mathematically the equivalence is. So that's why I'm not sure what role the cosmological or the matrix quantum mechanics plays is somehow related. Because here in this matrix model, there's just n. There's just n, 1/n, expansion, and you get these numbers, purely combinatorial numbers. And that n is related to this mu to this, which means that basically the next one minus 1 to the b minus 1 at every genus. But okay.
Sorry, one more question. If you took the simple one matrix model, you took its dual, and you put a Euclidean circle, that would also be a cigar.
You put its dual meaning?
Meaning the bulk. You take the, you look at the bulk and you put it on, that would also be some sort of cigar.
You mean just
finite temperature black hole.
Finite temperature black hole, yeah.
So sort of similar to the kind of thing you talked about,
yeah,
but not exactly the same, right?
Yeah, I don't know the connection to that. That has all these non-singlet modes or something. Right?
But that, I mean, just on the same footing, the C11 partition function is a function of B,
correct,
right?
Correct,
which gets related to your topological string. Right? So that partition function was obtained purely from the singlet.
Yes, correct.
So it doesn't see
So
the
it doesn't, black hole.
Yeah.
So the C11 string, you can consider scattering of not just discrete strings, right? General movement string.
You mean in general, if you didn't have this sort of acceptable radius thing, yeah.
So then, is there an analogous continuum?
I don't see one.
On
yeah,
on the side.
I don't see. Maybe you have to go away from this level 1 theory, because that's when you get continuums. The SL2R at level K has a continuum. Somehow level 1 has this very special discreteness.
So Rajesh, it's you take the 4 Lagrange scattering amplitude C1 and just evaluate the E1, E2, E3, E4 with energy and discrete values.
Correct.
Then
That's what I think gives you.
I see. So that corresponds to some topological theory.
That's right. Yeah.
So the same formula, but you evaluate them.
I think so, because I don't think the winding modes really contribute.
I think it's in the same sense of what I just mentioned, that even the partition function is a function of mu.
Right.
Right.
Doesn't know about the
topological string.
right.
Right. So,
Right.
so one can take derivatives of that to get some correlation functions.
So what about in loops? In loops, don't other momenta run?
Yeah, in loops, if you were to this thing, probably there will be other momenta that will be this thing. So, so here you basically, I mean, the way the partition function was computed was through the matrix quantum mechanics at finite radius in the time direction, and then later people. So these papers, for instance, which computed that S matrix, were all using the free fermion description of the matrix quantum mechanics. These papers, for instance, they were just looking at free fermions and their scattering with. So here you could do it at all genus. In fact, Gross and Klebanov first, I think, wrote down the partition function, I think, at arbitrary genus G for any radius. And then these people generalized it to, I think, scattering amplitudes for the tachyons with different momenta. So this, as I said, in the end, I want to throw away the superstructure, this thing. This is, for me, a crutch to verify this duality, to try to argue that these numbers are the same as that. So it's like it's evidence for the duality.
Sorry, but I didn't understand the conclusion. So is the scattering amplitude of this theory the same as what Gautam was saying, just working at these things? Or, I mean, then why don't other momenta run in loops?
I think for genus 0, certainly, I guess you can distinguish, but for higher genus, yeah, I have to really go back but I don't know if
but you can take the full answer and restrict the energies.
Yeah, external energies, but then
External energies.
internal ones, yeah. No, but I think here it's not a continuum. It's only the discrete one.
Decoupling, even at the level of one to many, other things don't, because some special, I don't know, Kepner-Witten kind of decoupling.
Unitary 6 achieved. Because the previous thing was unitary.
But suppose the coupling happens to be that it couples to as 0 to be
Changes, everything changes.
everything is 0. This is somehow decouples. Genuinely,
Yeah.
that's what must
I
happen.
have to go back and look at the sequence one literature on this thing exactly, these papers which really compute the scattering amplitudes and how
Because in the in the 3-level scattering amplitude, which we have computed from the fermion
in flat space.
in plastic, there there were phase space things which use continuum energies. So I'm just wondering how that will now go with discrete stuff. That's related to, I think, she will comment also about the internal legs. Whether you can draw two diagrams at all satisfying the momentum convolution. So I don't know how that.
Okay, we can talk about it. I won't be using any of this very much. It's something I should also go back and look more carefully into the guts of this and you can tell me more about the flat space. Okay, so that this sort of indirect chain which sort of tells you that these are this matrix model. So almost everything in this chain here, like from this matrix model to here, this to here, these are well established in the sense that they are. This is clearly something that reproduces the partition function. These are not some fancy dualities or anything. They are just sort of ways of rewriting the worldsheet theories in terms of each other. So this is so this is see, but as a sanity check, and I want to just here to tell a story that which is relevant since I'm in Bombay. That when I was a graduate student in 1995, I had come one summer to Bombay, and I had come here just so Sunil was my host here, and I still remember very well. I was in his house. He had made a very nice lunch for me and everything, and then we were chatting. He had just, I think, written this paper maybe, and I was working on something called the master field and for my thesis. But I don't know how we just started chatting and this thing. And then we did some small calculations that over the next few days, then all while I was here. And we observed something which we thought was very strange, which is that there was this matrix model, which I'll show you the form of it. At some point, it doesn't look anything like this Gaussian matrix model. But at that time, we even wrote up a note which said you look at the Gaussian model and you compute the 1-point function, just raise n to the n. And you can write down a combinatorial formula for the 1-point function at all genus and so on. And then there was this W infinity solution of the two-dimensional string theory that Sunil had. And we just observed that the tachyon amplitude, again, in that theory, is the same as this Gaussian matrix model. But we had no idea why, but it was a very non-trivial coincidence that there was this thing. So it was very satisfying now, 27 years later. And you can see, I don't even have I didn't even have the tech file of this. I found it somehow in some old folder of mine. It was one of these black folders we had in Princeton, I think. And it was quite déjà vu in some sense. And I wrote to Sunil, and he also didn't have the tech file. It would probably have been just lost in the ether. But this thing. But anyway, so this was a sanity check. But now it's something we understand, and why this must be true, and why it must be true more generally for this whole set of correlators. That so this is, by the way, the matrix model is. I don't think any of you right. And yeah, at that time probably hadn't even written, but several of the same identifications we had noticed at that time. Anyway, so that is a story particularly apt for Mumbai. So
it's also an advertisement for Dropbox.
Tomorrow Dropbox will be taken over by something else, and that's it. It'll be gone. So no, once someone told me paper lasts longest. So it's good advertising for me. So anyway, so that is the part about the verifying the duality. And I just want to give a sketch of how we are thinking about it as a derivation of these correlators over here are given by certain correlators here, certain correlators in the A-model. I'll just be very brief here, but I can say more later. But I'll just to give you the basic idea. So as I said, if we want to drop all that's equal to 1, all that's structure, just now that we have strong evidence that these correlators, these set of numbers are the same as these set of numbers, or these set of numbers, how do you show that they are the same? And how do you make it manifest that they are equal? So firstly, there's been this whole machinery. So this will be now more contemporary in some sense. This was all too retro. There's been this whole development, which many of you have been studying, the SYK model, probably are familiar with, about these topological recursion relations that been developed by Eynard and collaborators. So that's a very powerful machinery, which tells you, given a matrix model or a matrix integral, how to generate, gives you a sort of a recursive relation for higher genus correlators and so on in terms of starting, let's say, some tree level or disk amplitudes, 2-point functions and so on, initial data. And it's all encoded in terms of geometry. And the geometry is, for the matrix model, is the Gaussian matrix model is sort of the simplest matrix model, but there's a kind of what's a spectral curve, a Riemann surface associated with it, which is given by this formula. So you see, forget about this for the moment, but I wanted you to see, of course, that the quality of these two, the B-model, the Landau-Ginzburg potential. But if you were just Eynard-like person and you looked at the Gaussian matrix model, you would associate with it this spectral curve, which is this Riemann surface. And this spectral curve has, what is this spectral curve? By the way, the spectral curve is nothing very fancy. It is basically the Wigner semicircle distribution. If you eliminate Z and write an equation for X and Y, effectively, it's a quadratic equation for Y and X. And so Y squared plus X squared is, you shift some variables. It's basically the Wigner relation. So that's what this spectral curve is. So it's a sort of, if you wish, that's the target space geometry that you can associate. with this matrix model. And this whole topological recursion machinery relies on computing certain quantities on that Riemann surface.
Sorry, Rajesh. So the T2 is
just the number. Is
support of the
yeah, exactly. It will be related to mu or yeah. It's basically the question of the Gaussian. You can scale it away if you want, but I keep it there for a specific reason. But
And when we study matrix models, we sometimes look at this quantity, which is 1 over z minus zi, sum over zi. Resolvent.
Yeah, that's the first of these sort of things. You can see that they are kind of like this. You take traces of these. So the basic quantities here are basically things involving these now connected resolvents. Like someone was saying, I think maybe Sandeep was saying about how in the SYK, the two-point function of density correlate. That's the simplest case where you have like two resolvents.
So X are the eigenvalues.
In some sense, in this picture. So there is a whole machinery now, well generated and well used even for these matrix models, which generates for you. So these WGNs are in some sense generating functionals for these correlators. Right? You just expand. Sorry?
In the SYK context, the kind of observable kind of trace of the minus number time.
Loop operator. That's another Laplace transform or something you can take up. Yeah, you can. That's a different basis. Another set of observables. If you were to look at those, depending on your purpose, you might use one or the other. That's related to the resolvent. Related to the resolvent.
X is just a complex. It's just a number.
I mean, it's a X of Z is a coordinate on the Riemann surface in the complexified space of the eigenvalue distribution.
Yeah. In that context, those are sort of natural because one thinks of M as the Hamilton. So is that picture at all that?
I think it may be. I mean, yeah, I've been asked this question: what is the result of all these level spacing? And it's certainly mathematically similar. It's a different kind of quantity we are looking at, but. And you can apply, for instance, for the SYK, there is a spectral curve, which is in some sense also related to this. It's sort of the P(1), the limit as P, from minimal models as P goes to infinity. So there's, yeah. So I haven't thought deeply enough about this and this thing to make any useful statements, but certainly the mathematical machinery is very similar, and there may be a useful connection to think there, because, yeah.
That's also that's a kind of double scale.
If you go to the SYK thing, that sine Z kind of spectral curve that you get, that's a certain limit that you take of these things. This is in a way the opposite end of that, but the same machinery applies in, But what I want you to focus for the purposes of so supposing you were a matrix model person, these would be natural things you would sort of construct. And what I want to say is that, and in fact, Eynard himself had rewritten these, and that part has not been used very much in the maths literature, but he has, following Kontsevich actually, he had expressed these things as integrals over moduli space of certain what I call characteristic classes in moduli space, generalizing them. It has a sort of a very general description for any spectral curve to write down something like this. But it's a very, I think the reason no one has used it is very non-transparent. In fact, it involves two copies of moduli space and everything. At least in this particular case, I think you have an interpretation of that. And it is because he just writes it as some integrals over moduli space, but where they come from and all that is not, I think, something he looks at. But I think it's very natural to think of it here in terms of this as generated by a matter coupled to gravity. And the matter in this case is this some field which has this potential. And typically in these, you get contributions from the extrema of this superpotential when W prime is 0. And you get 2 branch points, which are the 2 endpoints of the eigenvalue distribution, the cut. So normally in the double scaling limit, you zoom in onto one cut, one end of the cut, right? You just zoom in onto this end here. But now we are interested in the whole thing. And so there are 2 branch points. That makes it more complicated. That's why the double scaling limit is in some ways easier to see what is this thing. But so this makes it complicated. It seems to make it complicated. And if you use the machinery of Eynard, you get some very non-transparent looking integrals over moduli space. But if you think of it as essentially coming from 2 copies. So if you were to think of a matter theory coupled to 2D gravity, then you can do the integral over the matter part and left with an integral over the gravity modes, 2D gravity modes of moduli space. And that matter part will get to contribution, will be essentially localized onto these 2 critical points of this. So you get, so in a way you can actually interpret the answers that Eynard has, and found these expressions here, but you can write them as what you would get from, if you were to compute this sort of matter-like correlator and integrate out the matter piece, you'd get essentially 2 sets of contributions from the 2 different branch points. Z is, so you should think of this Z as really the spectral parameter here. And there are 2, you see when you just differentiate, you get a quadratic equation and 2 solutions, Z equal to say plus minus 1, plus minus T or something. And those give you precisely the sort of integrals that Eynard and so on. So what I want to, this thing here is that this matrix model through this machinery, essentially this one is a purely matrix integral machinery, which generates this auxiliary space-time from the eigenvalue distribution. And then you compute, you can express those. There's an algorithmic way of expressing them as integrals over moduli space, which can be then viewed as coming precisely from the matter part, which I think Eynard did have. But Eynard typically has one branch, one copy of moduli space associated with each. So with each branch point. But now we understand what those 2 copies are. They are essentially coming because you integrated out the matter. So that's sort of the sketch of the B-model derivation.
And we must go on to the center side, but just out of curiosity, so at least in the double scale limit of such curves, you then get these recursion relations in the volumes of ordinary oneself. Correct. And here it is for 2 copies.
In this case, you get for 2 copies essentially because it depends on just the number of critical points of this presenting.
The rest of the spectral curve, in a sense, connects them.
Yes. So the 2 endpoints, and if you were to, of course, have 4 cuts or something, then you'll have 2 cuts. You'll have 4 copies of moduli space and so on.
It really is like the full SYK model, because that also has the 2 ends of the discrete.
But you zoom in on
in the double scale.
Yeah,
but you keep everything.
Rajesh, to me another thing. So if you integrate out the matter field,
then you have the molecular gravity.
Exactly.
R1 of R.
You mean just the usual bosonic fields, if you integrate out, you'll get you get the D minus 26.
Certain number of
Correct.
and then you have some
R1 over box R.
So that theory can be written as a
Liouville-like theory, yeah.
that solutions with it of course has the homogeneous solution. I'm saying that if you are just looking at all classical solutions of this theory, then there are solutions with branch points.
All classical, if you just write down the Liouville equation and look at the solutions,
Yeah, so these things have been interpreted, in terms of H series by written in our context. But I'm saying that Liouville theory has solutions
which have this classical distribution.
So I wonder whether things that
all solutions are to be intermediate in terms of two chiral fields. Any two holomorphic and anti-holomorphic functions. So you can manufacture any chiral field like whatever singularity structure is, and you get a solution of Suri.
I seem to remember branch.
No, or
More
just only two
solution of a Liouville equation, a classical Liouville equation, you can write it in terms of
These are some things with the intervals and so
on. This is with the soul. This is with the soul. I got it.
So, well, you're talking about the homogeneous.
Yeah, that's what I'm saying.
This is somehow the opposite, in the sense that the branch points are associated with this potential, the matter. This is sort of, if you wish, the solution. But it's, And then, at least, if you want to connect it with the Eynard thing, Eynard writes it as integrals over moduli space, which come from, which just depend on the branch points of this.
Sorry, Rajesh, I have to ask you, this is so exciting. I mean, so you think all this then suggests that, even away from the Sarchenko-Stanford double scale limit, you should have a gravity interpretation.
I would say
some generalization of
for a general matrix model, yes, I think there will be always a maybe any non-double scale matrix integral, I think always have.
Maybe then just even for SYK, like a couple of.
But it's we're talking different from the Sarchenko. There the matrix model was the matrix is a dimensionality, but was 2D.
Right.
But here it's we're talking of
the interpretation is different. Maybe
the correspondence with Sarchenko is to take a particular large limit of matrix.
I think the mathematics is the same.
But what is
the expansion there is for them the actual 2D gravity wormhole expansion.
Exactly.
So we interpret that here as a world sheet expansion, but they interpret it as a space time.
World sheet is the space time.
Yes.
That's where 2D gravity.
okay.
Right.
With that,
I think that's correct. So, because people have written down these more general, Witten and all wrote some matrix model and all, right? With some complicated potential.
Yes.
Yes. So, in principle, I think it should be. But I wouldn't want to. It's a little bit beyond the horizon, I see, but it should as an extrapolation. There's an A-model picture, which is, we need the thing that probably connects more directly to the things I've been doing earlier, because I told you that the A-model geometry is this coset space, and there's a momentum deformation. So how do you maybe try to arrive at this A-model geometry? And I think there's a complementary way in which we can try to derive the A-model picture. And this is related to, this is a problem, as you can see, I've been obsessing for 25 plus years, but 10 years or 12 years ago with my student Roji, we had, we had tried to connect this with certain Yeah, okay. So let me not go into all the details because there's a lot of background here. But there's a very beautiful combinatorial interpretation of these numbers in terms of covering maps. Holomorphic covering maps from the world sheet of genus G to a target space, which is a P1 sphere, which is the same sort of sphere, but with 3 branch points. This is in mathematics, there are these so-called Belyi maps, which have a lot of very important number theoretic significance and everything. But so it's a counting problem, and the counting problem can be related to a permutation problem. Counting holomorphic maps can be reduced to a problem of permutations, because each branching point corresponds to some cycle structure. And if you have 3 branch points, you basically have 3 permutations. And there's a very beautiful map. I think it should be a beautiful connection, which I think should be known. I think Itzigson and others had pointed out long ago, and then we were also this thing. And then Sanjay, I talked about this once at a South African meeting where I think where Sujamit was there. And
10 years ago.
Yeah. And so it's a very beautiful mapping because basically the combinator, it's very, it has to do, there are 3 permutations. Why are there 3 branch points? And there are 3 permutations associated to them. Very easy to understand.
Then you just talk.
Yeah, so the third one is sort of determined. The product of the 3 is identity, correct? They're not all 3 independent permutations, but there's a very natural interpretation for those permutations in terms of Feynman diagrams, these big contractions. The 3 are associated with vertices, edges, and faces. So with the vertex is the external insertions. So in free Gaussian theory, you have traced M to the L1. So there's a cycle of length L1 because you permute when you have a vertex with L1 things, you're kind of permuting the indices, the color indices as you go around. So that's with vertices. That's one permutation. Then faces. As associated to each face, there's a permutation because you identify various edges with this thing. And then each edge is a simple permutation, which is the usual big contraction, which identifies 2. So it's a permutation of length 2. I have one big contraction from here. This I identify with this. So actually, associated to any Feynman graph is a set of 3 permutations. One associated with the L1 to Ln, the structure. Another associated with the edges, which is always of length 2, permutations of length 2. And the third one, as Abhijit said, is just determined in terms of the other 2, which is what the faces do. So that's what, in a way, when you do big contractions, that's what you're doing. You're counting those different ways of permuting, how many different permutations you can have.
Permutation or cycle structure?
Cycle structure permutations. Yeah. So branch covers are given by cycle structures of permutations, and you want to see how many of those you can have.
And so I understood the permutations. But tell me again, what is this relate? Branch covers of what is?
So, so you have your world sheet, like the usual triangulation of a world sheet, and that has
the genus of the surface.
The surface.
The Riemann surface created by
the world sheet or the Feynman diagram. Okay. And then there's a target space which is this P1. You can think of it as the genus of the representation. Yeah, exactly.
And if it were more, there were more branch points, there's a nice extension of this map.
I mean, you can, of course, all I'm saying is that the free field Feynman diagram or a matrix diagram is associated with 3 permutations. And those are these. So any graph that you can draw in a Toft sense will be always associated with 3 permutations and to do with these 3 branch covers.
L1 and 2 LNR is the cycle lengths.
Cycle
Of one of them.
of one of the permutations which is associated with your external operators.
Yeah.
Trace m to the n, but that's fixed. And then you sum over all the big contractions, which is basically summing over all the different other ways in which you can have cycle lengths of length 2, which is how you associate 2 different things when you do a big contraction.
So what structure of these permutations tell you the genus of your manifold above?
What structure? It is the what you call the Riemann-Hurwitz formula, the branching structure. Because you have, so there is this thing, right? So each summation of, so L1 means that above each of these, there's all these, there's a branching L1, which is mapped to a single point. So you can, if you triangulate, so you can, so the genus of this is 0. So V minus P of the target space plus F is 2. And then you see how many pre-images there are, and it's what is the Riemann-Hurwitz formula, which tells you the V of the world sheet. One thing I just want you to note, which, yeah, so, okay, so this is all known stuff, and we have used this to kind of, I had tried to propose at that time a somewhat very close A-model dual to the P1, but now this becomes much more of a compelling picture because this holomorphic maps is precisely what in the ADS3 tensionless string theory with Matthias and Lawrence Eberhard, we had argued. So these L1 to Ln, so if you look at what are the physical observables here, they can be classified from the world sheet point of view. They can be classified in terms of the SL2R representations with precisely j equal to half and with the spectral flow of L1 by L1. So this is actually what in this old paper of Sujay and Samir Murthy and Yantros, they had shown that what Sunil and Kumran had shown was they didn't know about spectral flow at that time, but really post Maldacena Uguri, we know that SL2R, the set of physical states, you have to really include the spectral flow, and that's true for this coset theory as well. If you compute the world sheet theory, so the correlation function here is very close to that of the SL2R, I mean the ADS3 tensionless limit correlator that we studied, which for the same reasons that the spectral flow sector of spectral flow L is related to a branch covering of degree L. So you get a spectral flow of L, and then moreover, there's a momentum background here. There's a momentum background. That's why, I mean, you might, when I said about tachyon scattering amplitude, so these were related to tachyons of momentum minus L1 minus Ln in some convention. But obviously by momentum conservation, because this is just a free boson, by momentum conservation, it would be 0 unless there was something to soak up the momentum. So, and that's why I've been always saying there's this deformation. So here in the background, there is a positive momentum T2. That's what all this deformation always, so in this SL2R theory, there's a momentum 2 background I have to turn on. It's not the coset, but it's a marginal operator, e to the I root x, root 2x, which is the thing which is the momentum. And then that soaks up all the momentum. So you'll have L1 plus L1, Ln should be equal to that many, you have to pull down that many powers of momentum 2. And you see the momentum,
There also you have some
It's like that, yeah, it's like that a bit. But there is the Q root phi.
Gravitational dressing of the identity operator.
Yeah. In which one?
This square root of 2. Or
yeah, e to the I root 2x. Background that you turn on.
See, that one saying just in the if I take the x as the Liouville
no, but this is not the Liouville. This is the other one, the free function.
Other one.
Yeah. In fact, the momentum 2 operator is the one which has no Liouville dressing. This is the purely marginal operator which has just e to the I root 2a.
So that's a cosmological constant. No, it's not the cosmological.
No, it's that.
This is the one with the just with the matter field.
Yeah, just with the matter field.
Okay.
Yeah, it's because of the.
See, normally with that we use RKX.
Yeah, you have e to the ik pi and then there's some e to the ik. So there's some factor here. I think it's like k minus 2 and k like something. That's the marginal. That's the physical operator. But for k equals to 2, this is not there, and just you have this one here.
Yes.
So these modes, are they winding?
No, they're momentum modes. They are the same momentum modes as the.
So momentum in which
in the x direction.
In
the compact boson, if you wish.
So the time direction.
Yeah.
I see. But the spectral flow creates momentum in this time direction. That's what it does.
The spectral flow creates negative momentum, if you wish. Yeah. And the 1 unit of, I mean, yeah, if you by some positive unit, if you spectrally flow, that's like creating negative momentum in the.
So states with momentum are repelled from the tip of the cigar. So they live far away. Is that right?
They'll have support, yeah. You minimize that. This thing, I think they'll have support if you're very
asymptotically.
Yeah.
Okay.
So that's what I wanted to say here is that effective, and we have to I think, as I said, we see all the ingredients and we can see the thing, but we have to completely nail this down. I think but you see this branching associated with this momentum 2. I mean, this 2, which is the big contraction, is really the same 2 of this momentum. That's what I want to say.
Oh, I see.
Because the big contraction is a cycle of length 2. You pull down precisely these many momenta, L by 2, right? L is just summation Li. Momentum conservation tells you that you need to pull down. That means that's what big contraction also tells you, that you need to pull down exactly that many big contractions. And yeah.
Sorry. So now in this story, the time is Euclidean, right? The cigar time is Euclidean.
Cigar time is Euclidean.
So when we say momentum, it's exactly Euclidean.
Correct.
So winding is not conserved because it's a cigar.
Yes.
And now you've turned out a background for momentum. So momentum is also not conserved. Both are.
Both are not conserved by the background, yeah. But you can think of it as, yeah. So that's why you can have a non-zero correlator with, say, negative momentum.
Interesting. I mean, yeah, right.
Yeah. So it's but the L1 to Ln to be interpretable as a momentum, you know that for any L1 to Ln there are non-zero correlators. So something has to soak that up. And in fact, in this branching picture, these are precisely the one. So in this presentation, to answer something Gautam was raising earlier, here, these covering maps, that's another mathematically beautiful fact, which I think is seldom not appreciated enough, is that these branch covers exist only at very special points in the moduli space. these are respectively, and they're very nice points on the moduli space. They are what I call a certain kind of lattice-sized points on moduli space. And this is why, as you take, I don't know if I have a slide on that.
So I think it's just because the sphere with three functions doesn't have model. So if you ramify over it, then you will get only those points, right, in higher inner surfaces.
Yeah, you will get on the moduli space, there will be only certain points which admit those maps. Yeah.
Even if you have 4 points, it will have one-dimensional moduli space. So you carve out some one-dimensional.
Exactly. So this is why in ADS3 also we had the very similar phenomenon. And that the localization, the Lunin-Markov-like localization happened on very special points on the moduli space. And that's precisely what the worldsheet theory recovered. And here I'm claiming there's a very similar mechanism, again, for very similar reasons because of the SL2R at level 1, where the spectrally flowed sectors correspond to branch. Except now you don't have, because of topological theory, unlike in the earlier case where you had a position associated with each vertex operator. There was a position on the boundary, the symmetric orbifold, right? You consider twist operators at x1, x2, xn, and then you lifted them up. And so that's why there was no restriction there on the branching. Here, there's only, because everything, there's no position label. So that's why it's topological. So all these are at this branched over the same point, infinity. So anyhow, so there's this thing, so in both of these, you can recover this 2D gravity in a BMN-like limit where you take, say, all these L1 to Ln to infinity.
Very, very sorry. Yeah. In the previous thing, you had the A model and the B model.
Right.
In the B model, I think it's only special points in one.
Oh, so the B model is the Eynard or recursion.
One of them is special points in one space, the other is one in non.
Yeah, so that's what I was trying to say. But that's a bit not very invariant statement whether it's localized on moduli space or not. Is and in both of them, you recover the same thing in the double scaling limit. In this one, of course, it's an integral, and that integral goes over to the integral that Kontsevich and others had for matrix model. This one, in a more interesting way, it goes over to a continuum because all the lattice points essentially fill up the world sheet. This thing.
The recursion relations of Mirzakhani now to
which are the
volume.
Yes. Yeah. So that's what Eynard showed.
But you map to contributions from discrete.
I don't know for the general case. Yeah. Here I'm now making a case for the special matrix models. For the general case, I don't know how it will, because then you're deforming that matrix model away from the Gaussian quite a bit. So it's a little bit more
special.
You have some pictures, and you can. And so as I said, both in the B model and the A model, you can recover. Sorry, I'm using your infinite indulgence.
Localization at points in moduli space, from the point of view of the underlying two-dimensional theory on the world sheet. Yeah, so is this the statement that correlation functions are only localized at delta functions on the A model side, but they are more like normal field theories on the B model side? I see.
I mean, it would be very good to see explicitly how that is the case, but you can imagine some integral over moduli space, and that's sort of what happens in many of these things. That there are ways of writing things which are total derivatives, and you up to total derivatives, you can you get these singular contributions.
So there's no duality between the world sheet theories. There's only duality between the string theory.
Yeah. And in the world sheet theories, in the sense that there's a bit of symmetry between these two. There's a kind of a Hori-Kapustin like mirror symmetry you can define for between the A model.
Good, but then suppose I'm just not doing string theory, I'm just looking at 2D CFTs. Then how can it be that there's these two are the same theories where on one side they have only delta function localized correlators and the other side they're continuous?
So it depends, I think, on what you're really considering. I think it's so in this mirror symmetry. I think so the observables that you are looking at here and here. I don't think you are considering the same set of observables that would be mapped to each other in these two. The natural, because
so the operators don't map to each other. The operators don't map to each other.
I mean, what's a local operator in one description may not match to another. So could it be? I mean, very ultra-local correlators.
I mean, normally the statement of duality of quantum field theories is that the set of correlation functions are the same.
Yeah. So, but the question is, what is in a BRST? I mean, there are now in the string theory, you have to look at a
smaller set. So I can understand the string theories can be dual without the field theories being dual.
Yeah.
And I was asking, are the field theories dual?
Yeah. So these correlators in the field theory. Okay. When I
lost. So when you said the string theory is dual with the target space string,
the integrals over moduli, the correlator over moduli.
That answer.
Yes, that answer is
really BRST invariant operator.
Yeah.
You can imagine that the local operators and correlators are not the same, but once you integrate them.
Sure.
Yeah. Okay. But the question is now in the string theory, all you're looking at is correlators of
a very restricted
class.
Yes.
So it may be that, within that class, there is one integral, which is the function localized, but on the other side, it's another set of integrals, which are.
Yeah. Well, what was confusing is that Kapustin was claiming for just field theories, right?
Yes.
So, at the end of field theories, these two are just the same.
That's what I think.
And then you're saying that then the question of
presentation of one in which, because here also, when you go through this whole machinery here, where you look at this, so what the matrix models compute are always the integrals. They are not. When I say you can write these in terms of integrals, they are after you've integrated out the matter sector and then gotten something in this thing. But yeah, no. But a point well taken. I think that there's probably this thing of that there's a different set of members in that equivalence class which have this property.
So the map is a bit complicated.
Between the
I guess that's field theory.
Field theories.
Just the sphere, right? Just the sphere between. It doesn't have any. I mean, the operator that is being computed on the worksheet. What if you don't integrate over the worksheet parameter with the field theory? Just a 3-point function, right? With this function. I thought this
is in the target space. That's a different thing. In the field theory, you have in the field theory or the string theory, it's an endpoint function, endpoint vertex operators.
Oh, it's a map from higher genus surface to this.
To the vertex is the higher genus surface. Okay. So as I said, in the B-model, you can sort of recover when you kind of zoom into the edge of the eigenvalue distribution, it goes over to the kind of, so you take this BMN-like limit, you can very explicitly take it in these formulas for the B-model, and you see that it becomes just those of the minimal models, double scale string theory. These discrete volumes also go over into some kind of continuum volumes because these are counting lattice points, and it's like lattice points go over to the continuum. It's like the volume of a sphere you can count by just counting lattice points and taking some large limit. And this, in fact, the same kind of integral points on the moduli space are what appeared in this symmetric product, especially when we took the large twist vector, which is also some kind of these L1 to Ln was like the large twist in the Lunin-Mathur picture. There we have a very similar sort of a picture. Okay. So let me now just say something about the larger picture, which I want to which is just more or less a sketch only, but I think can be fleshed out. One of the other reasons, apart from it being a very simple toy model where you can see the thing, is that I think there's a very natural embedding of this in the full N=4 Yang-Mills theory. And in fact, it goes through an intermediate sector, which has been recently studied a lot by Gaeto and collaborators. So I claim this thing here. Let's say we take the B-model for simplicity, and there's sort of a relation to the conical. So this Gaussian matrix model, maybe many of you are familiar, has appeared in N=4 Yang-Mills in many contexts, famously with the half BPS Wilson loop, and later many other correlators in the half BPS sector. In fact, this sits as a subsector, as has been, I think, understood more recently, in a slightly larger. So these are just few numbers. But there's a slightly larger sector which gives you the chiral algebra sector, originally Rastelli and collaborators proposed, and which these people used this context of the so-called twisted holography. There's a chiral algebra subsector in which there are correlators that depend holomorphically on there are correlators on some two-dimensional plane inside the Yang-Mills theory, where the positions on the plane are related to the directions of the correlator, the field space. And they have a very nice feature that they obey. They are like correlators of currents in a 2D CFT, and that's why. So it has holomorphic information. And these people, they propose a sort of dual to that sector. That sector is a sort of a protected subsector, which is roughly like an ADS3 times S3 inside the ADS5 times S5. So you're looking at sort of a plane. So there's a dual, which is sort of an ADS3, but there's a sort of a conifold-like geometry, which is sitting inside here. And that's, I think, so there's a very natural embedding on this side also with this dual, I think, with this, which is then, and this may be the way I feel that you might see why is there a connection to the tensionless ADS3 CFT2. I mean, many things here are kind of very, have been prefigured in that. So where is that? I think maybe the say, and of course, this embedding is what people have, that's what Gaeto and others have been studying. So I think this has interest in being able to, if we can understand how these embeddings happen, and if we can understand how the string Belyi theory comes here, then you might want to then embed the matrix duality in this whole thing and understand that better. Yeah.
What actually the matrix is matrix embedding the matrix form the chiral algebra?
Oh, here there's a very precise map. I think this is there spelled out in these Gaeto papers, especially the more recent ones with his student Budzig. You basically, the chiral sector is where you consider some N=4 Yang-Mills scalar fields, which have some direction in SO6, but that direction is kind of correlated with the position. There's a particular further sub limit you can take where the position dependence goes away, and in the correlator. And then it's just a matrix model, and it's given by just a Gaussian correlator. So it's a half BPS sector that's given by Gaussian correlators. So it's the correlator analog of the Wilson loop, sort of half BPS Wilson loop.
These things don't, I mean, already at the chiral algebra still the coupling dependence drops up.
Yeah, exactly. So that's why here it's just a free theory. So yeah, so this is sort of was supposed to be my overview. I was going to show you this very nice calculation that I at least which maybe I'll just have some slides which I can maybe maybe I'll just show it by slides rather than go back to the blackboard. So I told you this very, I think this is was very crucial for us to realize why this Gaussian matrix model, and it's a non-intuitive matrix duality. So that's why I thought I would show it. And there are features which I think have some physical interest, which is to do with something I didn't talk about till now: open, closed, open triality. So I'll mention that maybe if I have 10, 15 minutes. Okay, so as I said, I want to, there's an exact equality between these matrix models. It's part of a general equality between these two matrix integrals. Well, there's two matrices, nothing. There's no more string theory, forget about anything. Just think of it, there's an n by n matrix integral of two matrices, some determinant operators, another n by q matrix integral with potential again, and two matrices A and B, and another set of determinant operators. I claim these two are the same. So, okay, I'm going to explain the notation.
Yeah, what is y in the first?
Yeah, I'll explain them. Yeah, so you can think of Y as a matrix, and it's a source matrix with along the diagonals, the Y I have used I. So I goes from 1 to, I think, n. Yeah. And then X is a similar source matrix with XA. A goes from 1 to Q.
Why is the left-hand side not? I'm a bit confused. K and M on the first one, K and M by n matrices. Very good.
And that's
But that determinant thing, there's a Q there. I understand the determinant thing involves these numbers just.
So here the source Y is up there, and here the source X is up here.
And both sides are functions of
T and T bar here.
Exactly.
Sorry?
What are T and T bar?
T and T bar. Here, yeah, here I haven't, let me come to that.
Yeah.
T is, I could have written this as 1 over G, some just coupling of this thing. And so forget about 2 for the moment. But there's a, the same. This is I mean, it looks very innocuous, but and you can actually show this very explicitly using this Hubbard-Stratonovich like thing, which is you first, let's say you start from here, you write this determinant as fermions. Then you you can integrate over M because you see it's linear in M. When I exponentiate this as e to the psi dagger s minus m psi, I can integrate out M. That gives a delta function that relates k to a bilinear of psi dagger psi. So I now can do the k integral as well. And then I can integrate in now. Okay. So I can do this. So this, yeah. I don't want to go into the maybe the.
But I guess my question was, how are the X's related to the Y parts?
They're independent.
I think they're not.
They're independent.
They're just completely independent. This is true for any x's, any y's.
Both are functions of x.
Yeah.
Both are functions of x and y's, and this is an equality.
Oh, yes.
And so we just very quickly, the T2 is the imaginary part of T. More generally, there is some complexity.
Yeah, more generally, you can think of a. In fact, in many of these, we play fast and loose with the context. Yeah.
So the first line is a function of the x's.
And the y.
And the y.
The x.
I guess the y is there.
Y is there.
Why is
There is source and y.
Fermions are integrated have both an A index and an I.
Exactly.
Yeah.
So, okay, let me give you the physical picture. I think that will make this. So, and this, I think, is an interesting physical picture for forgetting about all the just a minute. I want to think of this as n d-branes of one kind and q d-branes of another kind. So these are the AG degrees of freedom, and these are the KM degrees of freedom. And then there are fermions here, which are in the bifundamental of these. Okay, so there are these, and these. So it's a question of, and these matrix integrals can be viewed as the open string field theory of either set of branes, in which the other branes appear as determinant insertions or giant gravitons of the first set. So at this stage, it looks very symmetrical. And it is at some level, and that's why they are the same. But I can make it asymmetrical and in an interesting way. So this is the physical picture, and so all this integrating out this equality, and I'll maybe spare you the details. I can talk later if people are interested. But you can believe that you can get it by some integrating in, integrating out this thing, that thing, and then you write in terms of KM or AB. It's basically Gaussian integrals, and there's one other very nice aspect to this, which is that it exchanges graphs with dual graphs when I go from this to the picture to the other. Basically, that's what the I have these. And then I introduce essentially some fermions, which are in the, I introduce some psi dagger, psi A kind of fermions. These are in the bifundamental. So dashed lines are A, and colored lines are, solid lines are I, let's say, or other way around, whichever. This whole integrating out, integrating in picture has a very nice graphical interpretation that basically, in the process of having done that, you're exchanging Feynman graphs of the original theory to the dual graphs of the other theory. So I have one set of graphs in the original theory. I have only n by n variables, and I have Feynman graphs, sloped graphs like these. With this, when I integrate out, I'm claiming you'll get dual graphs in terms of the other dashed line variables.
I see. So the fermions are the intermediate stage.
Intermediate stage where there are the bifundamentals, and that allows you to integrate in, integrate out these things.
That's like doing worksheet T2. You exchange vertices with faces, right? Isn't it?
In some way, and that's probably
where you do this, vertex goes to face, and
no, I think it's more like a duality, because that's what effectively I want to say, that this one of these is the Yeah, there is something like that, I think.
In the second formula, was that Q by T2 or that's really N by T2?
That's actually N by T2. I shouldn't write that N. I should write it in a more symmetric way. There's a 1 over G. 1 over G is N over T2, or that can be written as Q over T2 bar or something.
Yeah, because T2 is something.
Yeah. Yeah, you can just put it very symmetrically in that sense. And
these are exact. This is an exact
integral. This is just an integral. It's an identity of integral.
And do you have some Argand limit in?
Yeah. So now I claim that the consequence of this is quite non-trivial of this integral. So, for instance, let me take this potential. This Vp of k is a potential of degree p, let's say. But I can take this, it's true for the same potential p that appears here. I could have taken any potential here. But let me specialize to the case where this is quadratic, so it's k squared on both sides. So if it is k squared, then you see that now I can do the integral over k. And I get something which is Gaussian in m squared, I'll get. And then there'll be this my and this determinant, this thing over here, right? In m, there's also a determinant in m. Now, a determinant in m, I can also rewrite it as this dk bar is what I've written there. It's basically the trace over q of x to the minus k. I basically expand this law. Okay, so in the Gaussian case, and if I, let's say, set y equals to 0, x and y are arbitrary, I set y equal to 0 here. So I said the source goes away. So then you see this side just becomes the Gaussian generating function of the Gaussian integrals, right? X is out. So that's where I need Q to be very large if I want to explore the space of all possible T's. Because only then, if I need as many independent, otherwise it'll be a Q-dimensional subspace of the space of all couplings. But if I put that y equal to 0 here, if I put y equal to 0, you just get some determinant of v. I have a here, which is quadratic, a squared, and I have an ab and minus ax term. Now, I can actually decouple the a and b integrals here because I now just redefine my b as b times a. I define b prime is b times a. So this ab coupling goes away. This was determinant of b that just becomes a determinant of b prime and a determinant of a factor, which I exponentiate and put it as a log. So I get a squared, that is this a squared, ax, that is this ax, and then the determinant of b term. It actually becomes what is called the Eynard integral, which is the logarithmic potential integral, which gives the Euler characteristic of moduli space. But anyway, forget about it. The b decouples, and the a integral, here you get this q bar. So the statement is an equality of these two. And this is precisely this Imbimbo-Muki matrix model. It had a logarithmic potential. It had AX. So the Imbimbo-Muki model was actually AX plus this, exactly this, with n equal to I mu. You get a log potential, you get this AX and this, but then there's an A square. So the Imbimbo-Muki model was really So this is the special case of the Ibimbomukhi model in which I have only the tachyon. So these were the generating function. This K bar was the so this is the function of T and T bar. So I differentiate with respect to T bar, I get negative momentum tachyons, and this T, I get positive momentum tachyons. But here I have only the one that I mentioned earlier, the one with the momentum 2 in those units. So this, you see, just at the level of matrix integrals, this is just an equality of the Gaussian matrix model. So anything you can say about the generating function of this is the same as that of this. And this is the theory that captures this equal to 1 matrix model. And this is the thing, this is the reason behind that observation that Sumit and I made 27 years ago, that that time we hadn't realized that there was this sort of way to see it, but it's basically the equality of these two integrals. They look very different, right? I mean, there's just a Gaussian integral, but this has a logarithmic potential, and this and that. So it just follows as a special case of that about identity. And I want to say, and we'll have this thing that this is sort of very, I couldn't go on and on about this aspect itself, about this whole open-closed open triality, which is the statement I believe which is true even in Yang-Mills or any theory, which is that there are two different open string descriptions of a closed string background. One in which the vertices correspond to the closed string insertions, and the other in which the faces correspond to the closed string insertions. I can elaborate, but depending on patience and stamina of people. But these, in this particular case, you see this. And in N equal to 4 Yang-Mills also, I think the same thing is there, because you see, these are like these giant graviton operators. So there's one description which is when from asymptotically flat space, when you take the near horizon geometry of E3 branes, you get ADS5 times S5. There's another description when you start from a tensionless ADS5 times S5, in which there are giant gravitons, ADS5 times S5, which then back react and kind of create the geometry. And there are two different open string descriptions, and that's what I'm claiming these two are. This is like tensionless limit, you're expanding around that. And that is the thing which corresponds to the giant. So basically all the giant gravitons here are back reacting to give you these potentials. These determinants are back reacting. If I have Q is comparable to N, then it will so that's all philosophy at this stage, but I mean, I think this is a very concrete realization of something I feel is more general.
While there are papers on the index of giant graviton.
Yeah, exactly. Right. So Samir and you're talking of the Samir and Gayoto and Imamura, correct.
There, this is very suggestive. I mean, because if you look at the giant graviton, like K giant graviton thing, computed by some SUK.
Absolutely. No, I think that's very much I discussed with Samir about this. I think it's very much in the spirit, and I think it can make it more precise. And in this embedding that I mentioned at the end, I think this is basically that subsector you're seeing. But these are the giant, I mean, in fact, there's a nice paper of Komatsu and others where they look at these determinant operators in N equal to 4 Yang-Mills and compute correlate.
But there, I mean, how previous there would be like one stack of giant gravitons, but in general,
you could have probably
116 PBS, then they have to use 3 stacks.
Yeah.
So the Weaver gauge theory that computes such things that has 3 modes. So that is slightly differs, right? Probably enriches this picture.
Yeah. So why did I draw it like this? Actually, there's a reason I drew it like this. This picture. These are compact branes, and these are non-compact branes. So I want to think of the branes that extend in the radial direction. Right. Those giant gravitons as the dual description. and the original ones are not extended. They are at the boundary, the original D3 branes. So in fact, I think in that cigar geometry, these are two different classes of branes. That's what I think we have. But there are these branes, and then there are these branes, which in Liouville theory would be the ZZ branes versus the FZZT branes. When you go kind of just to the Liouville part. But from the cigar geometry, I think they are both one-dimensional branes, but one is a non-compact one is a compact one.
So in case of variable flow, there is C6 till C3 is transfer. For every C, you will have this
exactly.
Yes.
This one was not clear. So these in ADS5 plus S5 context, these are along the
they go, there's a point like in S3, I mean the graph in S3, so they're point like in ADS, and so they go through the bulk of ADS.
Oh, they're point like in ADS, they're S3s on the S5.
Yeah.
Those are the ones.
Yes.
I see.
Because those are the determinant of the scalar field operator diagram.
So that's now this picture will have four symmetry, like a four-fold symmetry between four stacks, the original stack and the three stacks which are transfer straight. All of these will be symmetric.
So say which three stacks again?
So now in the D3 way you have this stack, and then there is a transverse C3, right? And then the generic giant graviton. So Imamura, for example, likes to think of a general 116 ppm giant graviton as coming from quantization of giant gravitons, which are RBB giant gravitons, which are either in one of these or the other. So all three he has, which spanning all the.
So that's why they are 1/16.
So all the symmetries would
broken.
One supercharge.
I see. Okay. Yeah. No, that would be more of a. There'll probably be
very symmetric picture.
Yeah. So there probably you'll have many more kind of descriptions, equivalent descriptions. Depending on which stack you use to kind of use as your open string description, and you integrate out all other modes.
So I haven't understood the giant graviton. So there are points in ADS, the spatial directions of ADS5.
Yeah, so that means in time. So they're moving in time. So in the ADS, they'll be like going like this.
I see. And then why did you say that these are the analog of the non-compact guys?
Because they're kind of going in the radial direction.
Oh, they move as points on the.
This is the asymptotic region, if you wish, and then it's sort of going.
It's optical.
Yeah, you think of it as the time direction. Then
you think of this as the time.
You're calling the
that's what I was not clear.
Yeah,
extended.
Exactly. In the Liouville direction, they're extended. These are point like in the Liouville direction.
No, but sorry, just to get it, the normal D3 branes which source the geometry are located at points in the radial direction.
Yeah.
Here, these guys are also points in our, that center of mass moves around. Is that the,
Yeah. They're center of mass. If you want the Coulomb branch, the other ones have been like that.
So, Rajesh, these are what we call giant gravitons, dual giant gravitons. Top that
Which is the one I tried. These are giant.
These are the giants.
These are the giant gravitons. Ones are the ones which are extended in ADS. Yeah.
Three-dimensional maybe.
And the other guys, the more usual giant gravitons, is that we start that is fine. And so you are not talking about that.
No. So that's what I think here in that last thing that I showed about the embedding. Yeah, so I think here these are these, and then they will be embedded in this chain in this way.
So, obviously, since you start with a topological or very zero radius ADS and then some back reaction producer. Say that a little bit again. What was the how does back reaction produce non-zero radius?
Because if you have Q of them, you see, you have Q, which is very large.
So you start like with one and you keep adding
more. So Q is of order, and then this back reacts, right? You'll get something which is of order n.
Yeah, so you're using the formula that gn to the 1/4 is radius.
Correct. Yeah.
And so you start with very small and then you keep
adding, and then that will deform it away from the tensionless limit to the.
So it keeps adding flux.
Yeah.
Okay. I see. So you think of the theory inside. So there are lots of, for instance, if I was thinking of dual giants, there were lots of dual giants outside, and you look at it from infinity, there's lots of flux. If you look at it from inside, there's almost no flux. So you build it from inside out.
Yeah, from small radius, you're going to.
Yeah, nice.
So that I think should be a general picture that somehow there is this other open string description which is more natural around the zero radius limit.
Which is also connected to this idea that all n are the same theory somehow.
All n, yeah.
Because you're building the theory of
n and q, and it's
one n from putting more brains inside.
Also Coulomb branch. Yeah, that is but here it's the transverse, but it's similar, spirit.
Right. There was one puzzle about or how many brains one can separate. It should be bounded by n, but
that is in the exactly on the S5 you can have maximum angular momentum n. So that determinant there is of size n.
Okay. But in those expressions there is some overall up to infinity.
Yeah. So here we are taking n and q everything into infinity.
No. So you keep n finite, but these giant gravitons is some of it
infinity.
Okay. So that was a bit puzzling. I didn't quite understand this. It is not quite resonating. Anyway,
you could do it. No, I think you could do it in that limit also. I mean, it depends on depends on what you're trying to do. Because here, as I said, this is true for any n and q. And then you can take different limits, and then the physical interpretation of the different limits, you have to see what they are.
And I mean, if you start with some SUN n equals 4, you think of these giant gravitons as this one of these planes going and becoming giant gravitons, right?
But that would be the Coulomb branch, but this is a different set because it's transverse to that.
Right.
So that's why I think the dual picture of the ZZ and the FZZT or whatever in the cigar picture, it becomes, I think, more clear that there's two different sets of brains. And I think that's very important there. Because otherwise, on the Coulomb branch, that would also be given by a usual Yang-Mills thing, right? But this description is a different description. In this particular case, I mean, there are just many things I can say, but there's this sort of thing arises from an open string field theory, this Codera-Spencer theory, which so Digraph, Vafa, Aganajek, Marcos, and others had these papers where they had these whole idea of this topological strings, compact versus non-compact rings, and both arose from this Codera-Spencer theory. These were modes of the Codera-Spencer theory, dimensionally reduced to this when the Calabi-Yau is a Riemann surface with some normal directions. So these are basically, so what are these A and B? Yeah, I should maybe have, they can be viewed as the two transverse directions. I mean, that in the Calabi-Yau language. If I think of it in the bigger embedding, these A and B matrices are effectively like the two of the transverse directions that you.
What do you mean? Sorry. So you have the 6 directions that they can.
Yeah, but the 6 you don't see in this BPS sector. In this BPS sector, you see only 2 transverse directions, one in the ADS and one in the sphere. Because this cigar is it's like you don't see the full ADS 5 times S5. So even the twisted holography was in a ADS 3 times S3 subspace of the ADS 5 times S5. And this is one, I think, even more. So it's like the cigar-like geometry. The SL2C has become SL2R mod U1. And so the number of transverse directions here are, so that's what the A and B are. A and B are these two transverse directions in this geometry. And that's the leftover of the fixed scalar and the whole Yang-Mills thing.
Once this, chiral algebra and then embedding this matrix model, Gaussian matrix model, the picture for n equals to 2, the final
n equals to
2, let's say.
Means SU2. No, when you say n equals to,
n equals to 6.
Okay, yeah.
You still have chiral algebra.
Yeah.
It's going to be this arbitrary side. So I'm just wondering if one gets the same type of.
No, good point. I can, yeah. I don't want to make more speculations here, especially if it's being recorded. So.
More questions? Anyone on Zoom? Not here.
The giant graviton matrix model is actually not a Gaussian matrix model in the normal.
Exactly.
Complex. It's a complex matrix model, but as was shown. Suchia. That it's basically you can make it upper triangular, and eventually it's only the diagonals which are important in
because sets are complex.
Yeah, because exactly.
But that's because the other triangular, the upper triangular components are already the grounds.
That's right.
So the
exactly.
elements are from the
I think I'm saying slightly a different thing because those are that's the matrix description in terms of the original open string. These, when you write the determinant operator and so on, the n is still, if I'm not mistaken, I think.
Yeah, I mean, there is
in terms of the
is
right, but so those are in terms of the original n by n matrix degrees of freedom. I'm talking of a q by q matrix degrees of freedom, which is Gaussian. One or the other. I'm taking the n by n to be the Gaussian, but then there's a q by q description, which is in terms of really the open string degrees of freedom of the q giant gravitons. You see, I'm not describing the giant gravitons in the original n equal to 4 Yang-Mills language. I'm talking of the open strings on these giant gravitons. On these giant gravitons, there are these AB degrees of freedom. Q by Q degrees of freedom, which are so I use that as an alternate open string description. And that is a very different one.
Yeah.
In general.
The kind of open string that Sumit even Andal had looked at. Open string excitations of the how we use it. Remember?
Not me. I think Anta certain thing. I think it's you're saying that there were the original set of D3 brains that had their open strings, and there is a description of the physics in terms of those.
And we know the
giant gravitons in that theory, they themselves can be considered as brains.
Right.
And their open strings also give rise to.
You can talk about an open string description in terms of those open strings alone after integrating out all the other open strings. That's what the Q by Q matrix, these degrees of freedom. So that these degrees of freedom, which are the same, and they're related by this graph dual. I mean, I have some weird speculations about what they could be in the n equal to 4 Yang-nulls also. There is this, and it's related to the thing that we were discussing in terms of this twister also there. Because there's this twister string theory of Witten's, and there's a way to write it in terms of a very similar sort of a thing. If you see, there's a cubic string field theory in twister scale. And and then the Yang-Mills interactions come out from the determinant of an operator from anyway, yeah, I can tell you more later. If, I think there should be something very similar, which is so the tension around the tensionless limit, there'll be a different way to expand around G Yang-Mills equals to 0. The other D branes are a good description around G Yang-Mills equals to infinity.
Mm. And is there some sort of sum over number of these giant gravitons? The other description?
Effectively, I guess, because you are kind of taking Q to infinity, and I think it's like not summing over, but maybe effectively you're like in a grand canonical and canonical sort of.
Yes.
Because, yeah. I mean, you can separate after all by going to the and those Y's and X's are the separation parameters. So you can sort of put them all coincident or separate them and effectively.
But the total number is n that somehow is put in.
So in the genus expansion, I don't think you see this, but for finite n, yeah. So genus expansion, because I think genus expansion. Neither n nor q really appear because you will.
They're being contracted.
Yeah.
Can I ask one thing? See, in the closed string description of either of those, like in the standard n, where n is the number that controls the open string description, that n does appear as a flux in the closed string variant, right?
But then when you have giant,
Now you're saying that if I have enough number of giant gravitons,
there will be a Q more flux.
then a Q more flux.
And you can.
But it's the same field which has the flux.
Yeah, D3 branes.
I think if you go to infinity, you'll see the total flux in everything.
I see, yes.
Rajesh, can you find what all the cases made this one the level of duality for your topics?
Something happened. You want to know this? This one you're asking here.
Yeah, how does this matrix model help you in this duality statement?
So, in two ways. One is it helped in just identifying these duals
The C equal to 1
through the C equal to 1 string theory, and because the C equal to 1 string theory is described by both these things. So therefore, you by the kind of
that's W is paths is still some non-trivial.
This was established in those old days, and so this is an equivalence. I think there's no you can more or less prove it. I think, and so. But then the second one is that this gives this other open string feature of this other the same. So how that fits in? Yeah, I think we have this sort of this thing that this other picture, and that's what I was trying to say at the end, that this other matrix model picture is really in terms of these other branes, these branes in both these pictures. So that's why. So this part, yeah. So you can forget if you wish about all this, but these two are two different open string descriptions of the closed string.
Does this might be sort of tangential potentially related. But that was still using this trick essentially and taking the Q going to infinity.
Right.
Yes, right.
Yeah.
So does that you use that to relate the Gaussian matrix problem?
Yeah. So I think this my collaborator Mazek, I think the history of this collaboration sort of goes to some of that, yeah, but I don't think we have revisited. At least I haven't revisited that thought, and I have only a nodding familiarity with it. Which trick was used earlier by this multi-scalar Cyberg and everything also. Yes. So I think the Akash and thing used that.
Actually, that is even quite pork.
That one, yeah.
Look at the later version, and the communication is somewhat about that. Because the problem with that in later version, they had to put something more. They had to do some kind of quenched averaging for me. I forgot how they actually fixed it, but I'll tell you why it is. What is the claim?
Well, the idea is that there was this small counter. So they wanted to think of the fermions as the SYK. Yeah. And if you take, so of course the problem is that there is no time. So we want to get the SYK model, we want the fermions as well. But they wanted to think of the Q, the label, the A label, right? That A label, the one has beats on discrete time.
Yeah.
But
essentially that's
I think maybe should have.
very detailed it doesn't. But they fixed it somehow.
It's a lattice of SYK models.
Yes.
That where time is that.
Time is that.
Yeah, if some of you can maybe even some paper, I'd like to. I mean, I haven't thought much about the respect here and this symbol. Clearly, there are many resonances. So you can, if anything strikes you, just it's like to understand a little better. Questions?
Okay.
Thank you, Rajesh.